What we're doing is looking at an isothermal process. In other words, isothermal. Isothermal means constant temperature. So we're going to look at the ideal gas with a constant temperature. So what does our ideal gas law tell us? Well, the right side of the equation, N, we've already said we're holding that fixed. K is a constant already. We're holding the temperature fixed for this isothermal process. So everything on the right side has a constant value. So if we set up our container over here with some value of the pressure, call it P1, and the volume V1, what we know is then that P1 times V1 must, switching to moles, must equal NKT, whatever the values are for these things. If we then move the piston, change the volume, we get a new pressure. We know then that the new values, P2, V2, what does this equal? Well, if N is not changing and T is not changing, we must get the same value that we had for the first situation. Well, if this equals this and this equals this, then we know that P1, V1 must equal P2, V2. For an isothermal process, the product of the pressure and the volume must remain constant. This result is called Boyle's law. Well, let's stick some numbers in here and see what it tells us about these quantities. Let's say for this isothermal process, where we know P1, V1 equals P2, V2, we start out with a pressure of our gas of 1 atmosphere when the volume is 0.500 cubic meters. But we allow the gas to expand. So maybe we take some of these weights off so the pressure is less, and, well, let's just say the volume increases. Let's not guess what's going to happen to the pressure. So we allow the piston to go up. What's going to happen to the pressure? Let's imagine the new volume is 1.75 cubic meters. What's the new pressure that goes along with this gas? Well, from Boyle's law, P2 will be P1 V1 divided by V2, so divide both sides by V2. We have P2 equals P1 V1 over V2. P1, 1 atmosphere, V1, 0.5 cubic meters, V2, 1.75 cubic meters. Multiply this out, and what do we get? We get 0.286 atmospheres. We end up with a smaller pressure. Well, it's kind of what we said, what we guessed. We allow the gas to expand, a bigger volume, lower pressure. Smaller volume, bigger pressure. Okay, very, very good. That kind of makes sense. If we think that if we compress the gas, what's going to happen? Forcing it into a smaller volume, the particles are going to be hitting the walls more often. We end up with a higher pressure. So that makes sense. But this is assuming that we maintain a constant temperature. So when we move the piston, if the temperature changes of the gas, we've got to make sure to bring that temperature back to the original temperature, either by heating or cooling the gas, whatever we need to do to get it back to the original temperature. And then when we do that, the pressure will have, in this case, decreased. Okay, very good. Let's take a look at another process. What else can we do with this gas? We'll now look at what's called an isobaric process. This is where we hold the pressure constant. Isobaric, baric like a barometer, meaning what's a barometer? A barometer measures pressure, atmospheric pressure. So isobaric means constant pressure, constant pressure. So what we're going to do is, for whatever process we do, we're going to assume that our pressure remains constant. We're going to keep the same weights on our piston no matter what. So wherever the piston ends up, we'll assume we have the same pressure. Well, what can we change? Still, we're going to hold N fixed. So in this case, we can change the volume and the temperature. But now we've got things changing on both sides. What made it easier the last time was we had everything that was changing on one side, and the other side, the NKT, we knew that was constant. Well, let's put all the things that are changing on one side and everything that's constant on the other side, just like we had before. So let's divide by T and divide by P. So we'll divide both sides by P and T, and what do we end up with? V over T is equal to NK over P. Well, now n is being held fixed. For this process, the pressure is being held fixed. K is a constant anyways. So now everything on the right side is again a constant value. So whatever happens to the left side, it's going to have to come back to that constant value. So what we'll have is, again, say we start out with some initial volume and initial temperature, say V1 over T1. And then we change the volume and temperature, and we end up with some other values, V2 over T2. Well, that ratio has to equal the same constant, so these things have to be equal to each other again. And here we have the relationship of the quantities for an isobaric process, and this is called Charles's law. And it tells us how these quantities, the volume and the temperature, are related to each other for an isobaric process. Let's stick some numbers in here. For our isobaric process, we know V1 over T1 equals V2 over T2. Let's imagine we start out with our gas with a volume of 2.50 cubic meters at a temperature of 200 Kelvin. In other words, negative 73 degrees. So pretty cold for this gas. But then we heat up the gas so that the temperature goes to 350 Kelvin. In other words, around 77 degrees Celsius. Well, before we stick the numbers in, let's just think about this. We maintain a constant pressure in the gas. We heat up the gas. What do we expect it to do? Well, if the temperature increases, we know these particles are going to be moving around faster. They're going to be hitting on the piston harder. Well, that's going to push the piston up. We kind of expect the volume to have to increase for this higher temperature. Well, let's see if that's what happens. So what we're looking for is, what's V2? Well, V2 multiply both sides by T2. We'll have V2 equals V1 over T1 times T2. So V1, 2.50 cubic meters. T2, 350 Kelvin. T1, 200 Kelvin. Multiply this out, and what do we get? We get 4.38 cubic meters. And yes, we see that the volume had to increase. The gas had to expand for this increase in temperature to maintain a constant pressure. Okay, very, very good. Let's try one more. Well, what can we do? Let me just write down the ideal gas law again. We've got PV equals NKT. We are assuming that N and K are held fixed. We have held the temperature fixed, that was the isothermal. We held the pressure fixed, that was the isobaric. What else can we do? Well, what about if we hold the volume fixed? That's what we'll do. That's called an isochoric process. Let's take a look at that. For the isochoric process, we're holding the volume fixed, volume constant. In other words, just imagine we're going to hold this piston in place. We'll put some clamps on it, hold that piston in place so that the volume cannot change. Then we can change well, what can we change? Well, if this is fixed, if that's held fixed, and that's held fixed, and that's a constant, we can change the pressure and the temperature. So maybe we heat up the gas and then we see what happens to the pressure, or we cool the gas down and we see what happens to the pressure. Well, what I'm going to do is leave that to you as a homework problem. See if you can do the same thing for an isochoric process that we did for the isothermal and the isobaric process, and see if you could come up with a simple relationship between the pressure and the temperature for two different situations of the gas, assuming that the volume is constant. Okay, great. Well, is there anything else we can do? Isothermal, isobaric, isochoric? Well, yeah, we could also change the number of particles. Could we hold more than, actually before we do that, let's say we're holding N fixed. Could we hold two of the quantities constant? Could we hold the volume and the temperature constant and only change the pressure? Well, if we held all of these constant, if this is constant, this is constant, this is constant, this is constant, there's only one value that you can put in for the pressure to make this an equality. So you wouldn't be able to change the pressure. If you held two of these fixed, or say three with the N, then you wouldn't be able to change the pressure. We could change the number of particles, hold two of these fixed and change the number of particles. We could do that, that's possible. But Typically that's pretty straightforward. I'll leave that to you to see if you can figure that out. But let's imagine that we will change the pressure, the volume, the number of particles, and the temperature. Well, what's that going to tell us? Well, what we tried to do before is always put the constant values on one side. The only thing that's constant now would be K. So let's bring these over here. We'll have PV over, whoops, not N, sorry. Yes, N. We are changing N. N T equals K. Well, now K we know is a constant, so the value of PV over NT has to be a constant. So we could say P1 V1 over N1 T1 must equal P2 V2 over N2 T2. And there we've got kind of a very general relationship for the ideal gas that would work in any situation, because the only thing we're assuming is constant here is K, the Boltzmann's constant. Or we could write it in terms of R, and we get the same thing, but then we'd have the number of moles here in the denominator rather than the number of particles. Okay, but that's always something that could be done as well, because K and R are constants themselves. Okay, great. Now let's take a little bit more of a microscopic view about what's going on here. What I'd like to do is think about how the pressure is actually being created, so to speak, by the ideal gas. Let's look at that. Let's imagine we're taking kind of a very close look as to what's actually taking place on the container wall right here. We've got the gas over here. Here's the container wall. We know that the gas is going to satisfy the ideal gas law, PV equals NKT. So what's going on? I want to think about where this pressure is actually coming from. We've got these gases, these particles of gas that are coming along. They're hitting the wall, bouncing off the wall. The wall is changing the momentum of the particle. Let's assume that we've got an elastic collision. So the particle goes in and comes back out with the same speed, same magnitude of the velocity, same energy, but there has to be some force exerted on it. We might say, well, let's assume it's got some speed. We can kind of calculate how much impulse has to be exerted on it. Knowing how many particles there are, we can get an approximate average of how many of these collisions must take place. If we make an idea of what the area of the wall is, we can get an idea of what force is being exerted on the wall. We can kind of figure out, we can kind of calculate. We're not going to go through it. We're not going to go through the calculation, but I think hopefully you can kind of see that it's possible. And we can get an idea of some of the relationships between the quantities and the microscopic properties of individual atoms. And it turns out that the average kinetic energy of each particle is actually related to some of these quantities. It's 3/2 K times T. This is the average energy per particle. 3/2 kT. The total energy of the entire gas, if each particle has 3/2 kT, the energy in the entire gas, if there are n particles, the total energy will be n times this, or 3/2 NKT. That's the total energy of the gas. We sometimes write this as a capital letter U, and it tells us the total amount of energy that the gas has. It's the sum of all of the kinetic energies of each particle. If that's the average energy per particle, all we have to do is multiply that by capital N, and that gives us the total amount of energy. Well, notice NKT, that's the same as this. We could also write it in terms of the pressure and the volume. It would be 3/2 PV. That would also be one way of looking at the total energy of the gas. Okay, great.